Hello, so in this video we are going to go through the homework for theme 4, which is all to do with the normal distribution and the central limit theorem as well. So we've got here a random variable which we're denoting by the letter x. Now in this case we're not told what that random variable represents. It could be heights, it could be weights, it could be marks of people in a class. We don't know, and it doesn't matter for this question. We're just told that we've got a random variable which is denoted by the letter x, and we're told it has a normal distribution. Therefore it's a continuous random variable and it's represented by the normal distribution. So I'm going to start off by writing down the parameters of this distribution. So I have x, and it's distributed normally, so I write n, and I've got two parameters with a normal distribution, you remember. The first parameter is the mean, and we're told that the mean is 20, so that's the parameter that goes in the first position, okay? Now the parameter in the second position can change. It can either be the standard deviation or it can be the variance. In this course, it is always the variance, which remember is the square of the standard deviation. In other courses, in other books, it may be the standard deviation, but in this course, it is always the variance. So in this case, because we have the standard deviation of this random variable being 4, it means the variance, in other words, the number that goes in the second position, should be 4 squared. You can write that as 16, but I'm going to write it as 4 squared. Okay, so as long as you make sure that you put the variance in that second position. Now we've been tasked for the first part to find the probability that the value of this random variable x takes on a value greater than 20. So we've been asked to find the probability that x is greater than 25. So remember that because it is a normal distribution, therefore it's a continuous random variable, it doesn't matter whether it's greater than or equal to. I'm going to treat that as the same thing because it's continuous. Of course, if it was discrete random variables, such as a binomial or Poisson distribution, I'd need to be a little bit more careful. But because it's continuous and normal distribution, I don't mind whether it's greater than or equal to. I can treat it as the same thing. So in order to deal with this, I first of all need to standardize. In other words, I need to take this distribution, which I've got at the moment, and change it so it's represented by a distribution, which I'm going to call z. It's still going to be normally distributed, but this time the mean is going to be 0 and the variance is going to be 1, and therefore the standard deviation. So I need to work out how I can change this distribution, okay? So let's first of all find the value which I want to find, okay? So I want to find the probability that x is greater than 25, okay? So in other words, I need to take 25 and I need to standardize it, okay? So in order to standardize it, in order to change this value 25 to be using this distribution down here, I use the formula. Well, I use 25 minus the mean. Well, the mean in this case is 20. Okay, so this is kind of doing a shift. It's basically changing this distribution, distribution with a mean of 20 and variance of 4 squared. I'm basically shifting this distribution so it's now centered around 0. And I do that by taking away 20 from all my values. But then I also need to perform a scaling transformation so that each standard deviation is now worth 1 instead of 4, okay? So in order to do that, I just basically divide this value by 4, okay? And that does my scaling for me, okay? So let's actually stick this into a calculator. In fact, I could probably do this in my head because 25 minus 20 is 5. And if I divide that by 4, I get 5 over 4 or 1.25. Okay, so in other words, my value which I now need to look at should be the probability that z now, because I'm using the standard normal distribution, this one up here with mean of 0 and variance of 1, okay, has now got to be greater than 1.25. Okay, now I'm going to use the tables in order to do this. So remember my standard normal tables, okay, basically says, well, okay, what is the probability that z is less than, and I basically ask for how many standard deviations, in this case 1.25 standard deviations. But in order to do this, my tables are cumulative, okay, which means I can't work with greater than probabilities. I need to work with less than or equal to probabilities. So in order to do this, I'm going to convert this to a less than or equal to by doing 1 minus that, okay? So I know that the probability that z is greater than 1.25 should just be 1 minus the probability that z is less than or equal to 1.25. Remember, 1.25 says, okay, what's the probability that I lie more than 1.25 standard deviations from the mean, okay? So the 1.25 represents the number of standard deviations from the mean on this distribution. Okay, so now in a position I can pull up my normal tables. Okay, so here are my normal tables. Now I want less than or equal to 1.25. So I'm going to go to the positive tables, which are the ones down here. Okay, I'm going to find the 1.2. So I know I'm looking at this row here. And I want the 1.25. So I go across to the column, which starts with the 0.05. I find the intersection points. So the intersection point should be that value there. So I know the probability that z is less than or equal to 1.25, the probability of finding a value which is less than or equal to 1.25 standard deviations from the mean is about 0.90, okay, so 0.8944, all right? So I'll come back here, and I'll go here, so this is going to be 1 minus the 0.8944 which I've just found, okay? But of course, I don't want that, okay? I want 1 minus that, right? So if I do 1 minus that now, okay, 1 minus that should be about 10.56%, so the 0.1056, which of course I could write that as 10.56% if I wish, okay? So the probability, if I've got a random variable with a mean of 20 and standard deviation of 4, the probability of obtaining a value which is greater than 25 on this distribution should be about 10.5%, okay? Now for the second part of question 1, I've been asked to find the value of d, so it's a bit of a backwards question. I've basically been told, look, if I look, same distribution, okay, so the same distribution we had before with a mean of 20 and a standard deviation of 4, or variance of 4 squared, okay, I'm basically told that if I look for a value between 20 and some other value, which I'm denoting as d on this distribution, I'm told that the probability of obtaining the values between those 2 points should be about 46%, so the 0.4641. I've been asked to find, well, what is that other value? So it's 20 and something else. What is the other value that gives me the probability of obtaining a value about 46%, okay? So first of all, I'm going to do it the way which I would normally do it. So I'm very comfortable with finding probabilities between two values. Because I know in my normal curve, okay, if I just draw a very simple normal curve here, here is my mean, okay, so my mean is in the middle, it's 20, okay? And I know that I'm looking for a value between 20 and some other value, okay? So I'm going to denote this as D, okay? And I'm basically saying, look, I know the probability between those values is about 46%, my 0.4641, okay? So I need to find that other value, okay? Well, in order to find this, in order to look for probabilities on a normal curve between two values, okay, I can basically look and say, well, look, I know that tables are cumulative. So in other words, I can first of all look at all values up until d. So what's the probability of obtaining a value less than or equal to d, or just less than d is fine. Okay, so probability that x is less than d. Okay, but I don't want all of the values up to d. I don't want all of that region. Okay, so therefore I'm going to have to take away the region I don't want. That's the region up until 20. Okay, so if I take away the probability that x is less than 20, then I should end up with this probability here, okay? The probability that x is between 20 and d, all right? Now, I happen to know that that probability should be about 46%, so my 0.4641, okay? So therefore, I think I'm in a position where I can actually work with this now, all right? So let's do this. Let's first of all standardize everything, because I think it'll be easier because then I can look on my normal curves or my normal tables to find some probabilities to work with this, okay? So let's first of all standardize the 20 because I've actually got that value here, okay? So if I'm going to standardize it, I'm going to work out how many standard deviations from the mean 20 lies. If you know something about normal curves, you might already know how many standard deviations it lies, okay? But I'm just gonna go for it for practice. So I'm going to do 20. I'm going to take away my mean, which I'm told in the question is 20. And I'm going to divide by my standard deviation, which is 4, okay? Now, clearly 20 minus 20 is 0. Anything, 0 divided by anything is still 0. Now, that shouldn't come as a surprise, because what that's basically saying is that 20 lies no standard deviations from the mean. That makes sense, because if you look, 20 lies slap bang in the middle of my curve, because it is my mean, okay? So therefore, it lies no standard deviations from the mean, because it is my mean, okay? Now, if I just do the same thing with my d, obviously I don't know this value, so I'm not going to be able to work it out exactly, but I should still be able to come up with an expression which should give me how many standard deviations from the mean d should lie. Okay, so I'm going to say z is equal to D minus 20 all divided by 4. So take away my mean, divide by my standard deviation, okay? And I'm actually just going to work with that expression as it is. There's not much more that I can do with that, okay? So in other words, what I'm saying, if I convert this to be a standard normal curve, instead of working with x, if I wanted to work with z instead, I'm saying the probability that z is less than, well, if I standardize d, I get this. I've just done that. So d minus 20 over 4, okay? Minus, well, okay, how many standard deviations does 20 lie from the mean? It's 0. I've just worked that out. So the probability that z is less than 0, okay, should be equal to my 0.4641. All right, fine. Now let's jump over to my tables because there's a probability here that I can calculate. I can calculate the probability that z is less than 0. So if I bring up my tables over here, okay, and I find 0 on them, well, 0 is that value there. Now you should have had to look that up in the tables. I just showed you where it was anyway. The reason why it's 0.5 is because of the symmetry of the normal curve. So if you have a look at my normal curve up here, okay, if you have a look, I know that by symmetry, half of my value should lie on the left side of my mean and half of my value should lie on the right side of my mean. That's the reason why a mean is called a measure of central tendency. It's the value which should lie in the middle of my distribution. So therefore, I know the probability that z is less than 0 should be 0.5, okay? So I've got the probability that z is less than d minus 20 over 4, okay, I'll work with that in a second, but then I minus 0.5 from that because I know that probability, the probability that z is less than 0 is 0.5, that should be equal to 0.4641. Okay, now clearly this is the thing that I want to calculate now, okay, this is the thing that I want to calculate. So here's what I'm going to do. I'm going to add 0.5 to both sides because then I'll just be left with the probability that z is less than d minus 20 over 4 should be equal to, well, if I add 0.5 to both sides, I get my 0.9641, okay? Now all I need to do is actually look in my tables and say, okay, which value, okay, how many standard deviations should I be looking at if I'm looking at a value which is 0.9641 units of standard deviation from the mean? And I know that that's what I want because it's a less than probability. Obviously, if it was a greater than probability, I would do my 1 minus. But because it's a less than I'm looking for, I just need to look at how many standard deviations this thing corresponds to, my 0.9641. Okay, so let's come over here. I'm going to look in my tables. And I just simply need to look in this section of my tables, and I need to try and find as close as possible to 0.9641. So if I have a look, well, look, 0.96 is kind of in this region here. And I think 0.9641, I've got it exactly, is there. Now, if you couldn't find an exact value, if you couldn't find your exact probability, get the one which is closest, okay? You could try and do linear interpolation, but just find the one that is closest. In this case, we've got it exact, so we don't need to worry. And that should correspond to 1.80 units of standard deviation from the mean, okay? So 0.9641, my probability I'm after, is 1.8 units of standard deviation from the mean. So in other words, what I'm saying is that that thing, the probability that z is less than something, my d minus 20 over 4, that should be my 1.8, okay? So in other words, from the tables I'm saying that my d minus 20 over 4 should correspond to 1.8 units of standard deviation from the mean, okay? So therefore, I should just be able to solve this now. So if I solve this, obviously I should times both sides by 4 and then add 20. Okay, so d should be equal to 1.8 times 4. And then if I add 20 to that, okay, well, let me just quickly do it on my calculator. So 1.8 times 4, so 1.8 times 4. And then if I add 20 to that, I get myself 27.2, okay? So the value of d in this case is 27.2. Okay, so let's go through question 2 then. So the weight in grams of beans in a tin. Okay, so I'm going to start off by instead of saying, well, look, let's have to write down the weight in grams of beans in a tin every single time. I'm just going to denote that by the letter X. Okay, I can denote it by any letter realistically I like, but I'm just going to call it X, and I don't have to write it down every time. So X is the weight in grams, okay, of beans in a tin. All right, so then that way I can just write down X, and I know that that means the weight in grams of beans in a tin. I don't have to write that long sentence out every time I want to deal with it. And I'm told it's normally distributed with some mean and a standard deviation of 7.8. So in other words, I can actually write down the distribution, or at least partially write down the distribution. So I know x is normally distributed. I don't know the mean, but I'm just going to let the parameter, the mean, just be represented by the letter mu. Okay, so mu. And the standard deviation is 7.8, which means that the value that goes in the second position is 7.8 squared. Because remember, in this course, we always deal with the variance as the parameter in the second position. Okay. Now we're told that given that 10% of cans, of tins, contain less than 200 grams, okay, so given that 10% of tins contain less than 200 grams, find the value of mu. So first of all, let's think about this sentence here. The 10% of tins contain less than 200 grams. What that means is that if I'm looking for the weight of beans in a tin, so the x, okay, if I'm looking for that value, the weight of beans in a tin, to be less than 200, I'm told that that should be equal to 10%. That's what that sentence literally means, okay? So in other words, this is a kind of backwards question, right? I need to basically use this fact to try and find the original parameter of my distribution, okay? Well, first of all, I think I can use my tables to kind of help me out here. Just remember that 10% I can also write as 0.1, and I'm going to write it to 4 decimal places just to be consistent with what's in the tables, because I suspect I'm probably going to be using tables in a second, okay? All right, fine. So the probability that x is less than 200. First things first, I need to standardize this 200. So I'm not working with this distribution. I want to be working with a distribution z, which is normally distributed with a mean of 0 and a standard deviation or variance of 1. Okay. So in order to do that, I'm going to have to basically take this 200. I'm going to have to take away the mean. I don't know what the mean is at the moment, so I'm just going to let it represented by the letter mu. So I'm going to do 200 minus mu, all divided by my standard deviation, which is 7.8, okay? Now, I need to go away and have a look in my tables, because at the moment what I'm saying is that the probability that z is less than equal to this thing, so 200 minus mu over 7.8, that thing should be equal to my 0.100, my 10%, okay? So I need to work out, well, how many standard deviations does that actually correspond to? I need to look in my tables. Now just remember, it's a less than, so let me write less than there, okay? It's a less than, so I don't need to faff around with 1 minus or anything, okay? Let's just jump straight into my tables and try and find 0.100 as close as possible. So let's come to this section of the table, which is my less than, so the negative units of standard deviation from the mean. And I'm going to try and find as close as possible to 0.100. Okay, so let's have a look. 0.100, well, I suspect we're going to be looking in this kind of region here. 0.100, yeah, I think the closest that we can get to 0.1000 is that value there, so 0.1003. Remember, I'm not going to faff around with trying to interpolate values in between. I'm just going to go for 0.1000 as close as possible to that, okay? So in this case, that lies negative 1.28 units of standard deviation from the mean, okay? So in other words, I know that this thing in here should be basically the same, okay? So my 200 minus mu over 7.8 should essentially be my, what was it, 1.28? Let me have another look. I've lost it again. Yeah, negative 1.28, okay? So that thing there should be negative 1.28. So now I'm in a position where I can actually calculate what my mu is, okay? I just have to solve this equation. So I should be able to times both sides by 7.8 and take away my 200 to get negative mu is negative 1.28 times 7.8, take away 200, which means if I just want mu, I'm going to have to multiply everything by negative 1. So it'll just be 1.28 times 7.8, add 200. Okay, fine. So if I stick all that into my calculator, okay, 1.28 times 7.8, add 200, I get myself 209.984. Okay, so that there is the value of my mean. That there is the value of my mean. Okay. Okay, so for part 2, I've been asked to find the percentage of tins which contain more than 225 grams of beans. Well, just remember that now I no longer have to work with this distribution because I actually know what the value of mu is. Okay, I worked it out in the last question. I found it's 209.984. So I now know, if I just want to write my distribution again, that x is actually distributed with 209 as the mean, 0.984 is the mean, and the standard deviation is 7.8, which means the variance is 7.8 squared, okay? And I've been asked to find the percentage of tins that contain more than 225 grams of beans. So in other words, I'm finding the probability that x has a value greater than 225. Well, this is a fairly standard question, okay? First of all, I'm going to use my table, so I know I need to be using a less than probability, okay? So in other words, this is going to be 1 minus the probability that x is less than or equal to 225. So my next task is to actually standardize this so I can use my tables. So in other words, z, so how many standard deviations does 225 lie from this mean of 209.984, okay? Well, I need to take away my mean, so my 209.984, and I need to divide by my standard deviation. So if I stick all of that into my calculator, 225 minus 209.984, divide all of that by 7.8, I should get a value of 1.93, okay? So in other words, 225 lies 1.93 units of standard deviation from the mean, okay? So I know that when I look it up in my tables, I'm going to be looking for the probability that z is less than or equal to 1.93, and I'm going to have to do 1 minus that in order to get the same thing as before, okay? So if I look it up in my tables, 1.93, remember, okay, so 1.93 is going to be on this side of the tables, 1.9 is here, okay, and I want 1.93, which is here, and I'm going to find the intersection point, so 0.9732, okay, so 0.9732. Now remember that I want percentage from this. So in other words, to convert that decimal to a percentage, just times by 100, that's going to be 97.32%, okay? In fact, it's not quite. I almost fell into that trap. Remember that I need to do 1 minus that, okay? So in other words, 1 minus that probability, okay, 1 minus that probability, so 1 minus 0.9732 should give me my actual probability, which is 0.0268, so I need to write that as 2.68%. So just really watch that, okay? I got a bit overexcited because I thought, hey, yeah, there's an answer there, I'm going to put that as an answer, but just remember, you make sure you need to do the 1 minus thing as well, okay? So 1 minus that should be equal to the 2.68%, which I'm after, okay? Okay, so let's have a look at question 2, part B. We're told that the machine settings are adjusted so that the weight of beans in a tin is now normally distributed with a new mean, but the standard deviation is now unknown. So it's, if you like, it's a bit opposite to what we were doing above. So the first question, we were told that the weight of beans in a tin, so x, is normally distributed with a mean of mu and a standard deviation of 7.8. So in other words, we didn't know the mean to start off with, and then we had to go away and find it. Now it's a bit of a backwards question. We're basically told we recalibrate the machine, we readjust the machine, and we now have a new mean and a new standard deviation. So we've basically now been given some new information that 98% of beans in a tin contain between 200 and 210 grams. We now need to find the value of the standard deviation, okay? So I'm actually going to give it a, I'm still going to use x, but I'm going to write down the new distribution. So I now know that the new mean is 205 and the standard deviation is sigma, which means the parameter that goes there has got to be sigma squared. Remember, it's got to be the variance, okay? Now we're told that if I'm looking for the probability of obtaining a value, so the weight of beans in a tin, between 200 and 210, which I'm going to write as that, so between 200 and 210 grams, I'm going to write it as that, as an inequality, and I'm told that that should be equal to 98%, so 0.9800, okay? I now need to use that to find the value of sigma. Well, if you like, this is a bit of the same question as I was doing in part 1, okay? So in other words, I've got my normal distribution over here, okay? I've got my mean slap bang in the middle, that's 205, and I basically know that if I'm looking at a value of 210, in fact let me draw that a little bit bigger, so if I know I'm looking for a value between 210 and 200, So let me get my 210 on the right side. So 200 and 210, if I'm looking for values between those two things, I know that that probability in there should be equal to my 98%, my 0.9800. So first of all, I'm going to standardize both sides of the distribution. So I'm going to standardize the 200. So I'm going to do Z is equal to 200. Take away my mean, which is 205, divide by my standard deviation, which I just know is sigma at the moment, okay? And this thing here, well, that should be 210. Take away my mean, which is 205, divide by my standard deviation, which I just know is sigma, and that should come out as 98%. Now, if I'm just doing a little bit of simplification here, this thing should come out as 5 over sigma, sorry, negative 5 over sigma, and this thing here should come out as 5 over sigma. Now this is really interesting. When you have a situation whereby the standard deviations should just be one negative of each other. So for example, this is negative 5 over sigma and this is 5 over sigma, which means that the standard deviations are the same, it's just one is positive and one is negative. So 200 and 210 lie the same distance of standard deviations from the mean, because obviously these two values are just negative each other. This is the negative of this. Okay, so when that happens, I know that 200 and 210 are symmetric around the mean. They lie the same number of standard deviations from the mean. Just one value, the 210 in this case, is above the mean, and the 200 value is below the mean. Okay, but they lie the same distance of standard deviations from the mean each time. So let's think about my curve. Well, look, I know that this shaded region, this region in here, should be 98%. And I know now that this region is symmetric around the mean, which means that this value down here and this value down here should also be the same area. Okay, well, what is that area? Well, I know the area underneath the entire curve should add up to 100%, which means that the whole area which is not shaded, the purple area, the area at the bottom and the area at the top, should be 2%. And if I split that equally among the two regions, I know this region down here should be equal to 1%, and this region up here should be 1% as well. So just thinking about logically, just drawing my curve and just being able to visualize it and realizing that 200 and 210 lie the same units of standard deviation from the mean, it's just one is above and one is below the mean, then I can use the symmetry of the curve to work out, well, okay, I know then that the probability of obtaining a value less than 200 should be equal to 1%. And likewise, I could have also said that the probability of obtaining a value greater than 210 should also be equal to 1%. So it doesn't matter which one I use. Now, funnily enough, I've just standardized this. Okay, so I'm going to use this one because it's a less than probability, and I know my tables work with less than probabilities really nicely. So therefore, I'm going to write down that I know that the probability that x is less than 200 should be 1%, so I'm going to write that as 0.0100, okay, so 4 decimal places, okay. And I know now that the probability that, if I standardize 200, I get my negative 5 over sigma. So I can write this as probability that z is less than negative 5 over sigma should be equal to my 0.0100. So now I'm in a position where I can literally work out, well, okay, how many units of standard deviation give me a probability of 1%. So if I jump over to my tables, I'm literally looking at my tables for 1%, or my 0.011. So I'm looking in here, and I'm looking as close as possible to 0.0100. So I think the closest thing I can get is that value there. Okay, so that's negative 2.33 units of standard deviation from the mean. That's the closest unit. That's the closest, which gives me a probability of 1%. So let's have a look. So negative 2.33. So the probability that z is less than negative 2.33 should also be the same as the probability that z is less than my negative 5 over sigma, which means I should just be able to jump straight in and say, okay, negative 5 over sigma should be negative 2.33 units of standard deviation. And from that, I should be able to work out what sigma is. Well, okay, if I just do a little bit of rearranging, I should find that sigma is equal to 5 over 2.33. Okay, so I've just literally times through by sigma and then divided through by my negative 2.33. The negatives cancel out. So if I stick that in my calculator, 5 divided by 2.33, I find myself as 2.15 as my value of my standard deviation. So 2.15 is the value of my standard deviation there. Okay, so let's have a look at question 3. The weights of bags of popcorn are normally distributed with a mean of 200 and 60% of all bags weighing between 190 and 210 grams. So, okay, I've got a couple of bits of information. Let's actually write it down before I start looking at part one. First of all, instead of writing down weights of bags of popcorn, I need to give that a letter, okay? Because I don't want to write down weights of bags of popcorn every single time. So I'm actually going to give it the letter Y, okay? Just because I always tend to use X, I'm going to write Y instead, okay? So I've got Y is represented by the weights of bags of popcorn. Okay, so bags of popcorn. Now, if you are going to do this, okay, so if you are going to represent your random variable by a letter, okay, always write down what that random variable is. It will help you, okay? I know we emphasized this sort of in the last video, particularly when we're looking at Poisson distribution, where the rate was defined by what you wrote down, okay? But yeah, just keep in good practice, always write down what that letter means, okay? So in this case, Y is the weights of bags of popcorn, and we're told that Y is normally distributed, okay? And we're told it's normally distributed with a mean of 200 grams. Now, we are not told what that standard deviation is, so I'm just going to write the standard deviation as sigma, and of course the parameter that goes there has got to be the variance, so in other words, it's got to be sigma squared, the standard deviation squared. Now, we're also told that 60% of all bags weighing between 190 and 200 grams. So in other words, if I pick out a value of a bag of popcorn, the probability that this bag of popcorn weighs between 190 and 210 grams should be equal to 60%. That's literally what that means. Okay, so let me say that again. If I pick out a bag of popcorn at random, the probability that that bag of popcorn weighs between 190 and 200 grams should be 60%. Because I'm told that 60% of all the bags of popcorn weigh between 190 and 200 grams. Therefore, I have a 60% chance, okay, 60% of those bags weighs between those two weights. So therefore, there's a 60% chance of picking out a bag which lies between those two weights, okay? So let's first of all start off by standardizing, okay? So I can find it on my curve. So in other words, if I standardize this, I get 190, take away my mean, which is 200, and I'm going to divide that by my standard deviation. And if I standardize this, well, I get Z is equal to 210, take away my mean, divided by my standard deviation. If I just tidy this up ever so slightly, this is negative 10 over sigma. And this one here is positive 10 over sigma. Now again, very similar to what we were looking at 2 part B, okay? Because I know, remember that Z represents the units of standard deviation from the mean that each of these values lie, so 190 and the 200 in this case. Well, in this case, because one unit of standard deviation is just the negative of the other, it means that 190 and 210 lies the same unit of standard deviation from the mean as each other. It's just one is below the mean and one is above the mean. That's the only difference. So one is the negative, the other just means one is above and one is below. Which means if I just draw a normal curve out, okay, I have 200 in the middle, and I'm looking for a value between 190 and 210. Well, I know that this region should be equal to 60%, and I also know that this region is symmetric around the mean, so it's not kind of pushed over one side. The reason why I know that, remember, is because the negative 10 over sigma and 10 over sigma, they're just negatives of each other, so the units of standard deviation from the mean tell me that this is evenly distributed. You can also see this around the curve, so symmetric. You can also see this about the curve, because if you have a look, 190 lies 10 units below the mean, and 210 lies 10 units above the mean, so you can also see it from the curve as well, okay? But just as long as you understand that this region is symmetric around the mean, okay? Well, have a look. I know that this region down here and this region up here should be equal to 40% in total. You happy? Because the area underneath the curve adds up to 100%. I've got 60% shaded in green, so that's 40% left over. I know because it's symmetric, this region down here should be the same as this region up here. So in other words, if the total region, the total purple regions put together is 40%, it means it gets split equally among the two regions. So this region down here should be 20%, and this region up here should be 20% as well. So what that means is that if I'm looking for a value of Y, which is less than 190, so if I'm picking out a bag of popcorn at random, I know the probability of obtaining a bag of popcorn which is less than 190 grams, that's equal to 20%, okay? Okay, that's literally what this region means. Likewise, if I look at this region up here, I'm saying, well, the probability that I obtain a value greater than 210 grams, okay, should also be equal to 20%. So in other words, I have a couple of inequalities that I can work with. Okay, so let's deal with this. So if I know that the probability, so I'm just going to work with this one down here, okay, just because it's a less than probability and I don't have to work with it. In fact, no. Do you know what? Because I looked at a less than probability in the last question, okay, I'm actually going to look at the greater than probability to show you get the same answer as well, okay? So in other words, I know that the probability that y is greater than 210 is equal to 20%. Well, look, I know that that 210 is 10 over sigma units of standard deviation from the mean. So in other words, the probability that z now, which remember is a normal distribution with a mean of 0 and standard deviation of 1, okay, is greater than 10 over sigma, that should give me my 20% or my 0.2000 as my probability, okay? Well, first of all, I need to convert this to a less than or equal to probability. So I'm saying the probability that z is less than or equal to 10 over sigma, well, that's equal to, well, 1 minus that is 80%, so 0.8000, okay? So just remember, I'm doing this as a kind of, I wouldn't do it this way, I'd always use this probability because it's already less than probability, but just to show you how you could use the other probability as well, just for practice, okay? All right, fine, so now I need to look in my tables and try and find the probability, the units of standard deviation, which have a probability as close as possible to 0.80000. So let's come to my tables, okay? So here are my tables, and I'm looking for 0.8000 as the magic number. So let's have a look. 0.8000, where have we got? 0.8000. I'm looking as close as possible. Okay, so I'm looking in here. Well, I think this value is as close as possible as I can get to 0.8000, okay? So that is 0.84 units of standard deviation from the mean, okay? So that is, so my 10 over sigma should be equal to 0.84 units of standard deviation from the mean, okay? So therefore, if I look at that, if I rearrange this, I get sigma should be equal to 10 divided by 0.84. If I stick that into my calculator, so 10 divided by 0.84, that should give me, well, it's 11.9. Okay, so 11.9 is the value of my standard deviation there. Okay, so before I just jump straight into part 2 of question 3, okay, I'm actually going to write down my new distribution. So I've now still got y, and I know it's normally distributed with a mean. Well, my mean is the same, okay, it hasn't changed, so it's still 200. But I've just worked out that my standard deviation, that's equal to 11.9. So therefore my variance is 11.9 squared, okay? So a shopkeeper finds that customers will complain if their bag of popcorn weighs less than 180 grams. So find the probability that a customer is going to complain. This is literally saying, well, okay, what's the probability of obtaining a value or obtaining a bag of popcorn which weighs less than 180 grams, okay? So I want to find that probability. Well, remember, I need to standardize this first because I'm going to be using my my normal curves, okay, my normal tables. So Z is going to be equal to, I'm going to take the 180, I'm going to take away my mean, which is 200, and I'm going to divide by my standard deviation, which is 11.9. So if I stick that into my calculator, well, I get negative 20, okay, divided by 11.9, that's going to give me, that's negative 1.68 units of standard deviation from the mean. So in other words, if I'm using my my Z curve, so Z, remember, is normally distributed, mean of 0, variance of 1, okay? If I'm using my Z curve, then I'm basically looking up the probability on my Z tables, on my Z curve. What's the probability that Z is less than 1.68? What's the probability of obtaining a value which lies less than negative 1.68 units of standard deviation from the mean, okay? Well, let's jump into my tables. Let's find negative 1.68. So I'm looking down here, remember. Negative 1.6 lies here, and I'm looking at the 0.08 column, which lies here. Just need to find the intersection points. So that's going to be there, I believe. Okay, so 0.465. Okay, so 0.0465. Okay, so that's my probability. So therefore, this is going to be equal to 0.0465. Okay, so that is the probability that a customer is going to complain. I'm going to leave it as a percentage because I think it makes more sense leaving it as a percentage. So there's about a 4.5% chance. There's a 0.65% chance of obtaining a bag of popcorn which lies less than 180 grams. Okay, so let's have a look at question 4. Past records show that the times taken to run 100 meters by children in a school can be modeled by a normal distribution. So first of all, I'm going to write down x, okay? So x I'm going to represent as my random variable, which is the times taken to run 100 meters, okay? So time taken to run 100 meters, okay? And I know it's going to be modeled by a normal distribution. This is what I'm told in the question. So x is normally distributed. The mean is 16.12 seconds. And the standard deviation is 1.60, which means the variance is 1.60 squared. Because remember, that's the parameter that goes in the second place of my distribution. Now, a child from the school is selected at random. I need to find the probability that this child runs the 100-meter distance in less than 15 seconds. So in other words, I'm trying to find, well, what's the probability that the time taken to run 100 meters, x, that's literally my definition, time taken to run 100 meters. What's the probability that the time taken to run 100 meters is less than 15 seconds, okay? Now just really watch here. It shouldn't ever be an issue, but always watch that your units are consistent. So because your mean and standard deviation is given in seconds, it means when you want to calculate the probability, okay, you also need to be working in seconds as well. So seconds down here. And likewise, because your definition is talking in meters, the time taken run 100 meters, you need to also make sure that they're talking in meters down here as well, okay? It's just something to watch. Okay, fine. So what's the probability that x is less than 15 given this distribution? This should be fairly straightforward. Let's first of all jump in and standardize. So I know that z should be equal to 15, take away the mean, which is 16.12, divided by the standard deviation, which is 1.60, okay? If I stick all of that into my calculator, so 15, take away 16.12, that gives me my negative 1.12, and I need to divide that by 1.60, which gives me negative 0.7. Okay, nice. So in other words, what I'm saying is that I'm looking for the probability of obtaining a value which is 0.7 units of standard deviation below the mean or less, okay? So that's the magic number. So in other words, I'm looking for the probability that z is less than negative 0.7. Okay, so what's the probability of obtaining a value which is less than 0.7 of units standard deviation below the mean? Okay, well, I'm going to jump into my tables. Okay, so I'm going to find my tables. I'm going to find negative 0.7. So negative 0.7 lies there, and I know the first one is 0.0 anyway. Okay, so that's fine. 0.00 rather. So that's 2.420. Okay, so 0.240. Okay, which if I want it as a probability, if I want to leave it as a percentage, that's going to be 24.2%, like so. Okay, so that works out quite nice. It's fairly straightforward normal distribution. Now, part 2 is getting into this thing called the central limit theorem. Okay, so on sports day, well, not quite actually. I think I'm getting a bit premature. On sports day, the school awards certificates to the fastest 30% of children. So in other words, if you're in the top 30%, you get a certificate. Okay, estimates 2 decimal places the slowest time taken to run 100 meters for which a child will award a certificate. Okay, so just be careful of the language here. What this is basically saying is that if you're in the top 30%, you get a certificate. So in other words, I want to find the slowest time that you could have run in order to still get a certificate. So in other words, you need to be this speed or faster, okay? Now just be really, really careful here, because if you're in the top 30%, it means you're running the fastest, okay? Now, to run fast, it means you need to have the lowest time possible. Okay, so because we're talking about time here, our definition of x is the time taken to run 100 meters. It means that you need to be looking at as small a time as possible. So in other words, I know that the probability that x is less than, well, I need to first of all come up with some time. So I'm basically going to say t is the time to run the slowest possible value. It's going to be the slowest time possible in order to still get a certificate. Okay, I'm just going to represent that as t. Okay, well, I know that if you're that speed or quicker, in other words, you need to be less than that time. Okay, so in other words, let's say for example our time was 10 seconds. That's the slowest time that you needed to run in order to still get a certificate. So therefore I'm looking at 10 seconds or faster, which means I need to be looking at times less than 10 seconds, if that makes sense. Well, I don't know it's 10 seconds, I'm just going to say it's t, okay, that's the thing which I want to find. What's the probability that I have still get a certificate if I'm this speed or faster, okay? So I want to find t in other words. And I know that's equal to 30% because people that run a speed less than t, in fact, I'm going to say less than or equal to t because I want to actually find out what t is as well. It doesn't matter because it's continuous anyway. But that should be 30%, okay? So in other words, if I run a time which is t seconds or faster, that's about 30% of all the children that run the race, okay? So this is what I need to work out, okay? Well, first of all, let's standardize. So I'm going to say z is equal to t, whatever it is. Take away my mean, which was my 16.12 seconds. And I need to divide by my standard deviation, which is 1.60. So divide by negative 1.60, okay? So now I need to find out in my tables, okay? I need to find, well, okay, what's the probability that z is less than or equal to my t minus 16.12 divided by 1.60. What value does that give me if I'm looking for 30%? Well, it's a less than situation, less than or equal to. So if I can just jump into my tables and look up the value of 0.3000. Okay, let's have a look. So I'm looking for as close as possible to 0.3000. Let's have a look. 0.3000, that's going to be somewhere in there. I think that value just pips it to the post, okay? So 0.3000, 30.15%, that's as close as possible I can get. So that's going to be negative 0.52 units of standard deviation below the mean or less, okay? So negative 0.52 is going to be t minus 16.12 divided by 1.60. That's going to be my negative 0.52, okay? Now I just need to solve this equation, okay? So, okay, let's multiply both sides by 1.6. So solve it over here. So if I want to find t, I need to multiply both sides by 1.6. And then I need to add on my 16.12. Okay, so let's have a look at this. So negative 0.52 times that by 1.6, that gives me negative 0.832, and then I need to add on 16.12. Okay, so that's going to give me 15.288. So in other words, to 2 decimal places, because remember, I'm asking for it to 2 decimal places, okay, that's going to be 15.29 seconds. So what this basically says is that because I know that 30% of people get a certificate, okay, providing me the top 30%, that basically means that t, 15.29 seconds, if I have a time which is faster than 15.29 seconds, in other words, lower than 15.29 seconds, I get a certificate. I'm in that top 30%. Okay, so hopefully that makes sense. I think this is fairly tricky. It's just making sure to think about it, because the temptation is to go for greater than because you're looking for the top, okay? But that's not true here because you're talking about time. If you're in the top 30%, it means that you have a time less than the 15.29 seconds that we've just found, okay? Okay, so now we're getting into something called the central limit theorem for part 3. So we're told that 10 children are selected at random. So for the first questions, in fact, all the questions that we've been looking at up until now, we've always been looking at just selecting one, okay? Now we're looking at selecting 10 children, which means that we need to find the distribution which represents the 10 children, okay? So in other words, I'm gonna write this as x bar. So I've got x is normally distributed, 16.12 is the mean, and 1.60 squared is the variance, okay? So this is just for one child, okay? They have a mean of 16.12 and 1.60 is the standard deviation. I'm now looking at 10 children, okay? And then I'm taking the mean time of these 10 children is less than 17 seconds, okay? So I'm taking the mean time of these 10 children. So in other words, I'm trying to find x bar, and in this case, x bar represents the mean of these 10 children, okay? It's still going to be normally distributed. Now, just remember, according to the central limit theorem, the mean should stay the same. Okay, so if I take 10 children, 100 children, 30 children, the mean should become closer to what the true population mean should be. Well, let's suppose that this mean was found, so the 16.12 was found by modelling and sampling good data. Okay, so let's suppose the 16.12 is a good representation of what should be happening at the population level. In other words, that shouldn't change. However, my variance and my standard deviation should decrease. Okay, how should it decrease? Well, my variance should decrease by a factor of n. If you remember in the lecture, we went through why that is the case and we proved that. Okay, so in other words, my variance is going to be 1.60 squared. However, it's going to decrease by a factor of n. In this case, 10. The sample size n is 10. Okay. So that basically means that my distribution becomes more peaked, okay? The variance decreases, okay? So I need to decrease it by a factor of 10. So this now is the distribution that I'm going to be looking at. Now I need to find the probability that the mean time of these 10 children is less than 17 seconds. So I want to find the probability that the mean time of these 10 children, the x bar, the mean time, okay, is less than 17 seconds, okay? So less than 17 seconds. Well, now it's exactly the same situation we were looking at before, okay? It's just the same kind of straightforward standard deviation and normal distribution questions, okay? So first of all, we need to standardize. So z should be equal to 17, take away the mean, which is still 16.12, but now I need to divide by the standard deviation. Well, if the variance is 1.60 squared divided by 10, the standard deviation is going to be 1.60 divided by 10, all square rooted, okay? So, sorry, 1.60 squared over 10 all square rooted. So, therefore, if I just tidy it up slightly, I just need to square root the 10, that's fine, okay? So let's have a look at this. Okay, so if I actually calculate this big horrible thing, so let's stick in a calculator. In fact, that gives me 1.74, okay? So remember, when you're working out units of standard deviation from the mean, because my tables are given as 2 decimal places, I'm also going to give 2 decimal places here. So in other words, if I want to work this out, because it's already a less than probability, okay, I can just straightforward look up in my tables, what's the probability that z is less than 1.74? In other words, what's the probability that I obtain a value lower than 1.74 units of standard deviation from the mean? Well, let's find my tables. Let's find my 1.74. So 1.74 being this set of tables. So 1.7, I'm looking for 1.74. So that row, that column, that's going to give me 0.9591. Okay, 0.9591. So in other words, the probability that the mean time of these 10 children is less than 17 seconds is 95.91%. Okay, so pretty much everybody should have a mean time of less than 17 seconds. Okay, so let's move on to question 5. So we've got the marks of students in a test are normally distributed with a mean of 65 and a standard deviation of 7. So let me write this down. Okay, so I'm going to represent X as the marks of students on a test. Okay, and ordinarily this would be normally distributed, so X would be normally distributed with a mean of 65 and a standard deviation of 7, which means the variance is 7 squared. Okay, now I've told that 50 students sit a test. Okay, find to the nearest integer the number of students who got a mark over 70. Interesting. Now, don't get confused here by the 50 students sitting a test for the first question, okay? All that says is that you may use this again in the future. Remember that you only use the central limit theorem if you are sampling. In other words, if you select 10 test papers at random, okay, and you want to find the mean of those 10 test papers that you select, okay? In this case, for part 1, you need to find to the nearest integer the number of students who got a mark over 70. So first of all, I need to find, according to my normal distribution, okay, I need to find the nearest integer the number of students who got a mark over 70. So I don't necessarily need to use the central limit theorem here because I'm not selecting test papers at random and then finding the mean of those test papers that I suggest, of those test papers that I select, okay? So I just need to find the nearest integer the number of students who got a mark over 70. So in other words, what is the probability, first of all, that X, the marks of students on a test, is over 70 in the first place. Okay, so greater than 70. So first of all, I'm going to standardize this. So I'm going to find 70 and I'm going to standardize it. How many units of standard deviation from the mean does this lie? So 70 minus 65, all divided by 7. So again, not central limit theorem here because I'm not selecting test papers at random and then finding the probability, the mean of those test papers. It's just simply saying, what's the probability that I have a student test paper which is greater than 70, okay? So 70 minus 65, that's going to be 5. So it's going to be 5/7, which is, to 2 decimal places, 0.71. Okay, so in other words, I know that the probability that x is greater than 70 should be, well, what's the probability that I'm looking for a value more than 0.71 units of standard deviation from the mean? Well, clearly, I'm going to be using the tables here, so I need to be a less than probability. So this should be equal to 1 minus the probability that z is less than or equal to 0.71. Okay, so let's first of all find this part. Let's first of all find the probability that I obtain a value which is less than or equal to 0.71 units of standard deviation from the mean. So let's jump over to our tables. Let's look for 0.71. So 0.71, I'm looking at that value there, which is 0.611. Okay, so 0.611. Now obviously I need to do 1 minus, so 1 minus 0.611, okay? Sorry, 0.7611. Okay, and if I do 1 minus that, so 1 minus 0.7611, that is going to give me 0.2389. Now that's just come out as 23.89%. Now I'm not actually finished here, okay, because I'm not looking for the probability of obtaining a test paper which is over 70, okay. Here instead, I'm looking for the number of students that got a mark over 70. So if I'm looking for the number of students, what I'm going to have to do is say, well, look, I know that 23.89% of students got a mark over 70, which means that I need to say, well, how much is 23.89% of the original 50 students that sit a test, okay? Because I know that 23.89% of all students that sit a test get a mark over 70. I need to ask, what is 23.89% of 50 to work out the number of students who got a mark over 70? So if I just work that out, that's going to basically be 50 times by my 0.2389, my 23.89%, okay? So that should be 11.945. Clearly, I can't have 0.945 of a student. However, I've just been asked to find to the nearest integer. Now, there could be an argument to say, well, strictly speaking, only 11 students got a mark over 70 because you can't have the 0.945, okay? But in this case, because I've been told to find to the nearest integer, I'm just going to find it as 12, okay? Because 12 is closer to 11.945 than 11 is, okay? So I'm going to say 12 students here. But to be perfectly honest with you, if you put 11 in an exam, in a test situation, you would have still got the mark, okay? So it's about 12 students who got a mark over 70. So part 2 then, John knows that 33% of students got a lower mark than he did. What mark did he get? And again, give your answer to the nearest integer. So it's a bit of a backwards question now. I'm basically given a proportion. I know, well, if I say that John's mark is J, okay, I know that the probability that the people on the test get a lower mark than John, okay, so the probability that X is less than J, where J is John's score, okay, that should be equal to 33%, okay, so 33% of people got a mark less than John, okay. So I need to work out what is John's score. Well, first of all, I'm basically saying, well, if I standardize this, Z should be equal to J minus the mean, which of course is 65, divided by the standard deviation, which is 7. Okay, that was given to us in the question in the first part. Okay, so I'm just going to work with this. I'm basically saying, well, look, I know that the probability that Z is less than this J minus 65 over 7. That's the units of standard deviation, okay, from the mean. That should be equal to my 33%. Now, if I want to say 33% as a decimal, that's 0.3300. Okay, fine, fantastic. So I need to look up in my tables for a probability which is as close to as possible to 0.3300. So let's have a look at that, okay? So I'm looking for as close as possible to 0.3300. So 0.3300, where are you? I'm looking in this region here. There you go. 0.3300, slap bang there. So that's negative 4.4. Okay, so negative 4.4 units of standard deviation from the mean. Okay, so this is going to be the j minus 65 over 7. That's my negative 0.44. Okay, so okay. Now it's just a case of solving this equation. So if I want to find j, I should times my negative 0.44 by 7, and then I should add on my 65. So if I just quickly stick that in my calculator, negative 0.44 times 7, okay, add 65, that should give me 61.92. Okay, so 61.92. Now I need to find it to the nearest integer. So in other words, John got 61.92 if I'm working exactly, but to the nearest integer, I know that John's score should be 62. Okay, so in other words, anybody that got less than 62 on a paper, that accounts for 33% of students. Okay. Now, part 3, 5 test papers are selected at random to be checked. Find the probability that the mean mark of these 5 test papers is below 63. This is where I use my central limit theorem, because I'm actually obtaining a sample now, and I'm saying, right, what's the probability that the mean of this sample, in other words, these papers put together, the sample put together, what's the probability that the mean of this sample is, in this case, less than 63? So, in other words, I know at the moment that my distribution of my test papers, so x, at the moment is normally distributed with a mean of 65 and a standard deviation of 7, which means my variance is 7 squared. Now, when I take these 5 test papers, I know that the mean of these 5 test papers should still be normally distributed. They should still have the same mean as the population, okay? Because of course, as by the central limit theorem, as you take more and more papers, the sample mean approaches what the true population mean should be. So 65 should be a pretty good approximation of the population mean. However, the variance, in other words 7 squared, should decrease by a factor of n. In this case, the sample size is 5. Okay, so this now is the new distribution that I'm going to be using. Now I need to find the probability that the mean mark of these test papers, so x bar, is below 63. Okay, so I need to find this. Well, it's already a less than probability, okay, so I don't need to worry about that, but I do need to worry about standardizing. So I'm going to do 63, take away the mean, which is 65, okay, and then divide all of that by 7 over root of 5, because of course I know that that's my variance, which I'm going to be using, and I want to use my standard deviation, so I'm going to square root that. Square root at the top becomes just 7, square at the bottom becomes root of 5, okay? So it's going to be 7 over root of 5. So let's stick all of that into my calculator. So I get 63 minus 65 on the numerator, and on denominator I'm going to do 7 divided by the square root of 5. That should give me negative 0.64 to 2 decimal places. So in other words, I'm looking for the probability on my z-curve of obtaining a value which is below 0.64 units of standard deviation below the mean. Okay, so if I look for negative 0.64 in my units of my tables, okay, so there's negative 0.6, and I'm looking for the 0.64. So therefore, negative 0.64 is there. So 2.611. Okay, so 0.2611. Sorry. Okay, so 0.2611. I could leave it as 0.2611. I'm going to leave it as 26.11%. I think that is fine. Okay, so there's your answer. Okay, so last question then. A certain type of chocolate bar is known to be normally distributed with a mean of 100 and a standard deviation of 5, okay? Sorry, mean weight. So the weight of these chocolate bars is known to be normally distributed with a weight of 100 grams and a standard deviation of 5. So first of all, I'm going to write that down. So x is my random variable, and I'm going to let that represent the weight of my chocolate bar. Cool, okay. So I know that this thing, so the x, is normally distributed with a mean weight of 100 grams and a standard deviation of 5 grams. In other words, my variance is 5 squared. Now, I'm told that a customer buys 25 chocolate bars at random. So already, central limit theorem senses should be starting to kick in here. find the probability, the mean weight, there you go, the mean weight, not just the weight, the mean weight of these 25 chocolate bars. So the mean weight of my sample is between 99 and 102 grams. So first things first, I'm going to have to redistribute my distribution, because I don't want one chocolate bar. I don't just want X anymore. I want X bar, the mean weight of 25 chocolate bars. So same thing as before. It's still going to be normally distributed. The mean should stay the same, okay? However, because I know by the central limit theorem, the variance of the distribution should decrease as the sample size increases, and the variance decreases by a factor of n. So in other words, it's going to be 5 squared over 25, which of course should just be 1. Okay, cool. So let's have a look at this. I want to find the probability that the mean weight of these chocolate bars lies between 99 and 102 grams. So as an inequality, I'm going to write it like that. That literally means the mean weight of my chocolate bars, my X bar, lies between 99 and 102. Now, first things first, before I go any further, I'm going to separate this into two separate inequalities, okay? So I know that this thing should basically be the probability that X bar is less than 102, take away the probability that X bar is less than 99. Now, if you're not sure where I got that from, let me very quickly illustrate this. I know it's going to be a normal curve because it's normally distributed. The mean is in the middle, okay? That's my 100. And then I'm looking for a value between 99 and 102. Okay, so I'm looking for a value between 99 and 102. So I'm looking for that value in there. What I'm first of all, because I know my tables are cumulative, I'm first of all going to look for the probability up to 102. Okay, so therefore I'm going to look at the probability up to 102, X bar less than 102. Then I'm going to take away the probability I don't want. I'm going to take away the probability up to 99. And that should give me the probability that I'm after. Okay, so let's look at this. First of all, I need to standardize. So I'm first of all going to work out how many units of standard deviation from the mean does 102 lie. Well, it's going to be 102, take away my mean, which is 100, divided by my standard deviation. Now remember, I'm using this distribution now because I'm looking at the mean weight of my chocolate bars, my 25 chocolate bars. So therefore, I'm going to be looking at the standard deviation is going to be the square root of 5 squared over 25. Well, that's going to be equal to 5 over the root of 25. Okay, so it's 5 over the root of 25. Now, of course, if you do that in your head, it's still going to be 1. Okay, so I get 102 minus 100 divided by what is effectively 1. Okay, so that should just be equal to 2. If I do the same thing here, I get z is equal to 99, take away 100, divided by the standard deviation, so that's going to be 5 over the square root of 25, okay? So again, that's going to be a negative 1, okay, fine. So in other words, when I look on my tables, okay, I'm going to first of all look up a value which is less than 2, okay? That's what my 102 corresponds to. It's 2 units of standard deviation from the mean, okay? And then I'm going to look up on my tables a value which lies 1 unit standard deviation below the mean. That's what my 99 corresponds to, 1 unit standard deviation below the mean. So negative 1. So let's first of all find these two values, okay? So let's first of all find the probability that z is less than 2. So probability that z is less than 2, let's find it. So there's 2, and it's 2.00, so therefore it's 0.9772. So 0.9772, that's the probability of obtaining a value less than 2. If I'm looking for z less than or equal to negative 1, or just less than negative 1, it's fine, it's the same thing. I'm going to come to my tables, I'm going to look up negative 1.00, that's my 0.1587. So 0.1587. If I do a quick calculation and subtract those two things from each other, so 0.9772, take away 0.1587, that should give me 0.8185. If you want to leave that as a percentage, that's 81.85%. So in other words, if I go into a shop and if I buy 25 chocolate bars of this type, which I know are normally distributed with a mean weight of 100 grams and a standard deviation of 5 grams, then I know that if I pick up 25 chocolate bars at random, the probability that the mean weight of these 25 chocolate bars lying between 99 and 102 grams should be equal to 81.85%. It's a pretty high chance that my mean weight of my chocolate bars, my 25 chocolate bars, should be between 99 and 102. And of course, as I select more chocolate bars, if I sample more chocolate bars, say 50 chocolate bars or 100 chocolate bars or maybe 300 or 1,000 chocolate bars, I know that the probability of obtaining a mean weight of these chocolate bars being between 99 and 102, in other words, the mean weight of my sample is between 99 grams and 102 grams, should get higher and higher and higher by the central limit theorem, because the variance of the distribution should decrease, okay? In other words, the probability of obtaining a value around 100 should be equal to more or less 100% as I select more chocolate bars, okay? But either way, for 25 chocolate bars, I know the probability of obtaining a value, a mean weight of these chocolate bars between 99 grams and 102 grams is about 82%, okay? So hopefully that makes sense.